Let's continue looking at some other examples that involve applications of exponential functions. This time we have a diver. There's the water level. The diver's going down, and as he goes down, it gets darker. The light intensity is reduced by 2.5% for every meter that he descends. We want to find the percentage of light remaining after the diver has descended d meters below the surface. So our dependent variable is percent of light left after we've gone down d meters. D is the independent. And so again, we start off with a pattern. The percentage of light after 0 meters, in other words on the surface level, that would be 100% light. So let's say 100 units. And every meter we go down, we know that our light is reduced by 2.5%. All right, in other words, the amount of light left is 97.5% of what it was before. So after we go down 1 meter, we have 97.5% of the light left, 97.5 units, I'm going to call it. Okay, so what I did not do going from here to here is I did not subtract 2.5%. I thought of this as meaning I have 97.5% of what I started with, and that calculates to this. And I say that because as we go down 1 more meter, let me just pull the calculator out here. I am going to have my starting amount of 97.5% light, and I'm going to lose 2.5% of it. In other words, I'm going to have left 97.5% of what I had before. And so I now have 95.0625 units of light left after going down 2 meters. So notice that this did not go down by 2.5 units. We took this previous amount, which is the same as all of this, and we multiplied it by another 0.975, which makes it to the exponent 2. So after going down 3 meters, I'm going to have the previous amount, and I'm going to multiply that by 97.5%, because that's the percentage of light that's left. 97.5% of this will be left. In other words, that's to the exponent 3. So to generalize this, the percentage of light after going down d meters is going to be 1,000 times our multiplier, and this exponent matches the number of meters I've gone down to the exponent d. It's exponential in nature. If I know how far down I'm at, I can get the percentage of light. And by using logs, if I know the percentage of light, I could work backwards and solve for d. This is going to represent a decay situation because our multiplier is less than 1. So if you start off at 100, the graph's going to go down like this as the value of d increases. Okay, so an exponential decay graph. Another example, half-life. In chemistry or biology, you've probably talked about this, at least the concept of it. Half-life is the amount of money that it takes for half of a given substance to disappear. Okay, so for example, a half-life of 80 means that it takes 80 days for half of the substance to disappear. Example, we have radioactive phosphorus, 32, and it has a half-life of 14.3 days. So after 14.3 days, half of my starting quantity goes away. And we want to write a formula for the percentage of this after n days. Okay? So we start off with a formula. Now as we're going through this, hopefully you're starting to pick up how this goes in terms of building the pattern up, and you're sort of kind of expecting what the final equation is going to look like. So we're starting off with our starting amount of phosphorus, which is, let's say, 100 units, 100%, however you want to look at that. And the first time I can actually do an accurate calculation is after, not 1 day, but after 14.3 days. And that would be 100 multiplied by a half. I would have 50 units left. I would have half of it left after 14.3 days. After another 14.3 days, which is 28.6 days, I would have the previous amount multiplied by another 1/2. So I would have that to the power 2, and that would be 25 units. And let's do it one more time. Another 14.3 days would bring us to 42.9 days, I think, which is 100 times a half squared, times another half for this next 14.3 days that's gone by, so to the exponent 3, and now I have 12.5 units left. So to generalize the formula, the percent of phosphorus left after n days is 100 times a half. All right, now this is n, because that's how it's defined, number of days, doesn't match this. But we know the connection between these two things. The number of days divided by 14.3 gives me this number. 28.6 divided by 14.2 is 2 multiplications. 42.9 divided by 14.3, sorry, that was 3 here, is 3 multiplications. So the exponent here is going to be the number of days divided by 14.3. Okay, so if we wanted to know, for example, how much phosphorus do we have, let's say after, let's try to go halfway between these two time periods, let's say 7.15 days. So I've got 7.15 divided by 14.3. I need my calculator to work this out. 7.15 divided. Now, just before I press the button, you might be wondering, if I've gone halfway between the times, am I going to get an amount that's halfway between 150? No. I get 70.7 units is left. And of course, the reason for that is that this is not a linear function. The amount is not going up in a linear pattern, it's going up in an exponential pattern. And this is once again a decay graph because our base is less than 1, so the graph's going to look something like this once again. Okay, there's less and less of it left as the number of days increases. Last example, population of frogs doubling every 20 weeks. At present there are 400 frogs in the population. Find the number of frogs after n weeks. Alright, instead of building this up with a pattern, I am going to try to just, based on my understanding of all of this to this point, see if I can jump right to the formula. The number of frogs after n weeks. Well, I've noticed in all the questions I've done that it's always started off with the starting amount, which is 400. And then the thing in the brackets is the multiplier. What am I multiplying by every time? Well, in this case, I'm doubling, so I'm multiplying by 2. How often am I multiplying by 2? Every 20 weeks. So my exponent, I want it to be 1. I want the exponent on this to be 1 for 20 weeks. Okay, I want 1 multiplication of 2 after 20 weeks. Well, if n is my number of weeks, 20, but I want the exponent to be 1, then this exponent's going to have to be n over 20. Okay, so for example, after 20 weeks, if I put n in for the formula, 20 over 20 would be 1. That would be 1 multiplication of 2, which would be 800. Okay, and so I have my final formula.